So we've got a situation here. A ball is being thrown up in the air and it's allowed to fall back down again. We're going to draw a graph of this in a moment, but this ball at the moment we can just identify what forces are being felt on that ball. Well, it's just going to be the only force that's going to be felt on it is the weight, and we can calculate the weight by the mass times the times gravity. Or we should really call this the gravitational field strength technically, but mass times gravity is fine for now. And then we can say, well, that therefore then also because in Newton's second law is F is equal to mass times acceleration. Now this we're going to say this ball has a mass m, and so the strength, so the force, the force which is the weight mg is equal to ma. So the m's cancel out. So that means that g is the acceleration. So the acceleration is down, okay? So now if doesn't matter where and this is the important bit, okay? It doesn't matter where the ball is, it's still going to experience the same force, it's still going to experience the same acceleration because the same mass, same strength of gravity. Yes, that's true, but to an extent. So basically we assume that the ball is near the surface of the Earth. So there is actually in reality, when you move away from Earth, the strength of gravity reduces slightly. Obviously, we know that when you think about it. When you get away from planets, gravity is less. But when I throw this pen up in the air like this, the strength of gravity, the force it feels there, is so similar to the force it feels there that you can just ignore it. You just don't even. It's the same. We basically say it's the same. So that's why we say it's the same. So G is the acceleration. So what we want to do now is think about, well, in different parts of the journey. So first of all, what's going to happen throughout the journey? So as you throw the ball up, it's going to be moving quite quickly just as it leaves the person's hand. Then what's going to happen to the velocity of the ball as it reaches the maximum point? And once it's reached the maximum point, what will the velocity be? And then afterwards, what will happen to the velocity after it reaches maximum point? So this is the first attempt at the graph of what it would look like. So we can see the first part is positive velocity because it's moving up. So we're going to say up is positive. That's fine. Well, it doesn't matter if you say up is positive or down is positive, as long as you're consistent. So we're saying up is positive. And we can see also that although at the same time as it going up, it's reducing in the speed at which it's going up. And eventually, it reaches 0, and that would be when it's maximum height. Now, the gradient of this this slope here is going to be the deceleration. So let's just label that here. Let's just point to it. So the gradient is equal to the deceleration. But the deceleration is just gravity, because the gravity is the acceleration. Well, the deceleration is just whatever acceleration is in the opposite direction. So at the moment, the ball is moving upwards, but the acceleration is down. So we call it deceleration because obviously it's not getting faster, it's getting slower. But deceleration and acceleration is the same thing. It's just that a deceleration is acting the opposite direction to the motion. So gradient is equal to deceleration, which is equal to g, which is this. In this case, g on Earth is 9.81 meters per second squared. Okay. So now we're going to try to work out. So afterwards, once it's reached the maximum height, let's just label that as maximum height. At maximum height, for the smallest possible amount of time, it is not moving, and then it starts to move in the opposite direction. So now you can see it's moving down, so it's got a negative velocity. And that negative velocity increases because it gets faster and faster and faster. The Question is, what does this gradient tell us? What is this gradient going to be equal to? So I'll pause the video there. All right, good. So this is now correct. So the gradient stays the same. Oops, the gradient stays the same for the journey up as well as the journey down. Now this is only assuming there's no air resistance. If there is air resistance, it does actually change. If there's air resistance, what happens is as you get faster, the air resistance increases, and when the air resistance increases, it actually reduces the overall force, which means it reduces the overall acceleration. When it's going down, on the other hand, when it's going up, it increases the deceleration because it's going to be you're already slowing down as it is because of gravity, and now it's going to slow you down even more with the air resistance. So it would end up like at the well, actually, no, it would decrease. So because the air resistance is going to be high for high speeds and low for low speeds. So that's much more complicated, but we won't do that now.